Welcome back to the linear optimization. We're going to talk about the simplex algorithm. In fact, we're actually going to talk about the single-stage simplex algorithm. The single-stage simplex algorithm expects us to already have a basic feasible solution at hand, and then we can continue. Without that, we need to do something more complicated, like the two-stage simplex algorithm or other algorithms, which we will talk about. But all of them have the single-stage simplex algorithm in the middle. So this is used as a subroutine for all future algorithms. Keep that in mind. Got chalk on my pie t-shirt. Oof. So we're going to start with a given basic feasible solution x0 and its corresponding basis. We'll set two flag variables, opt and unbounded, to no, essentially to say that we haven't found our optimum and we haven't determined that the space is unbounded. And specifically, the unboundedness is in the direction of the cost vector, so I can actually have an unbounded not low. If I end up being unbounded, it's because I can get whatever cost I want in the negative direction. And so I am not bounded below by a constant. We're going to have a loop which just repeats infinitely until we see that opt becomes not no or unbounded becomes not no. So we'll either figure out where we have our optimum or we'll find out we have become unbounded. If we look at our relative costs, Cj, if this is always non-negative, then what we have is we've satisfied our optimality condition. And so our optimum, we should say yes. That's all we'll do. And it'll spit us out of this loop and we'll be done. If we don't have the optimality condition, we have some relative cost which is strictly negative. We're going to choose that, and what we're going to do is we're going to pivot along this. Once I've selected my pivot column, we need to examine the entries xij in that column. If they're all non-positive, then what happens is that we can mark unbounded to be yes, because essentially what's happening when we do the pivot, we're going to compute theta 0 and find out that it is infinity, which means that I'm unbounded in this direction, and because I have strictly less than 0 relative cost, as I do these unbounded direction movements, I'm going to reduce my cost an infinite amount, as much as I want. So otherwise, at the very end, what we're going to do is we compute our theta 0, as in our pivot computation. It's from this set of fractions. It's equal to one of these fractions for a certain L being 1 to m, and then we pivot on this entry. It's essentially like in our tableau, we circle it, and essentially that means that I'm taking xj, I'm putting into the basis in the nth position. So I'm removing the nth basis element and placing xj into that basis. And what we'll do is we'll continue. When I do this pivot, what we're doing is we're finding a new basis. If theta 0 is 0, I haven't moved my basic feasible solution, but I've got a new basis. But if theta 0 is strictly positive, what that means is I'm creating a new basic feasible solution, and I've improved my cost function. I've strictly lowered it because the change is going to be dependent on Cj bar. So we want to say that this algorithm works, and it does work subject to a few things. First off, this step is where we have the least amount of control right now, or we have the most amount of flexibility, is one way to put it. What happens is that there may be multiple positions with strictly less than 0 relative cost. But perhaps we choose one, and then it ends up having theta 0 be 0. And that didn't change anything. And then I compute that again, and I see a new thing of relative cost 0, less than 0. And you might actually start cycling through where I actually have just been taking out and putting back in the same set of variables. And so what we need to do is build what's called an anti-cycling rule to select this properly. So we will talk in class about how to select such a vector such we do not cycle. And the other thing is, when do we know we're going to be finding an optimum or finding an unbounded set? So just keep in mind this algorithm as we think about a few notes. So remember our optimality condition in theorem 2.8 says that when our relative costs are all non-negative, that's when we have our optimum value. Okay? And that is, from that, we see that that's why we set opt equal to yes and we stop. In the algorithm, we may have multiple options for choosing j. So remember, all we need to do is have the relative cost at j be strictly less than 0. So to make that a concrete step and say, absolutely, this is the thing to pick, that method to break these ties is called a pivot rule. If I get to this step and I see that all of these values are at most 0, then if I were to compute theta 0, I'd get infinity. And then that really means that this feasible set, first off, this feasible set is unbounded, because I can continue having theta 0 go off to infinity, so I will never run into a boundary of the polytope. But also, this cost function will not be bounded below, because since my relative cost is negative, then this function decreases as theta grows. And so this value will go off to negative infinity as theta 0 goes to infinity. And that finishes how to perform a pivot. And that finishes our description of single-stage simplex. Next, we're going to go through an example of following the algorithm from beginning to end.